Can you hear me? Okay. So I have received your email. You want to ask something about, let me put the record and then share. Okay, can you see the screen? Okay. So we have this. You send me this file. What's the question? Actually, I'm not really understand your question. Okay. P3. I can't hear you. I think your connection has problem, right? Okay. So, uh, ah, yes. I think you have no problem to find the time derivative. You have no problem to find time derivative. Your problem, is it because of the, you can see my cursor, is it because of the del square? Del square, you need to have the z component. I mean the z. And then del over del t, you have no problem because del over del t, the time is in the exponent. And then E naught x here, at the moment we consider it is some sort like you can ignore, because E naught x here, E naught x actually is z dependence, but you take the time derivative for this term, so it is affect only the exponent. It will work only on exponent. But the del square here, you use the slowly vary envelope. Okay, my question is, now you are still work with the last semester. Am I right? You still work with the one that I mentioned in last semester. Okay, I think your project is based on the paper. Can you see this paper? I keep on mentioning this paper. And the one in last semester, you can just take it as some introduction to the conventional approach. But actually, you no need to pay too much attention on that, because the derivation there definitely is not suitable for the approach according to this paper. I think last time I do point out that uh, I think this paper, I think he did mention that for system with quite strong nonlinearity, are not so suitable to use the approach. I think when you work it here, the problem is about the z dependence, d over dz. Let me wait for a moment. Okay. So let me see. You try to. Okay. So for the E, actually your E is too small. I want to make it larger. Okay, actually the E here, electric field actually depends on Z and T. So it is something that b not x, okay, space, you have the exponent minus pi omega t, and the z part, you have if the wave is traveling, you must have this part, exponent I k z, because z is the direction of propagation. Okay, z is the direction of propagation of the wave, and then this is the polarization. The electric field is perpendicular to the direction. So x is perpendicular to z. Okay, so this one actually is x. Okay, this one actually is x. You can use x hat or I hat, x hat or I hat. So this direction is for this vector component, is for this E field, but the direction of propagation is z. Okay, so if you have this, then you no need to worry about this del square. Okay, this del square you can work on this. Del square actually, when you work, you cannot work on x because x is constant. This one will change sinusoidally because of this change. And then the del square will work on this. Okay, so if you want to understand, is it okay? I hope that I answer your question. So this is complex notation. If I write the real notation, I have to write like this. No, if actually I just thought I have something wrong. So actually I should write like this. Copy plus the CC. You know the CC is when you see the I, you change the sign positive, it will change to negative. The positive I here means that the wave travel to the positive Z direction. This one, it doesn't mean that negative, but somehow when you apply to the actual situation, when you apply to the actual situation, for example, if you have okay, let me say something. So this is real field notation, and we can write into complex form. It's like this. Okay, you can see the half here, right? So if you want to really write into the real field, then it is equals to half real. It is something. It is something that cos. Okay, it is something cos or sine. But it is better that you write in this form. Okay. So the positive ikz here, this is just assume that the wave propagate in positive z direction. So for example, if you have a medium, insert let me see.